try and introduce you to infinity operads. Right, so sort of, yeah, so what I want to do in the first part of the course is first we're going to briefly introduce operads without infinities, just so we're on the same page, and then discuss like two quite different descriptions of infinity operads. So one is the Lurie description, and then the other one is via dendroidal Segal tensors. Right, so in the first section I called from operads infinity operads. And I know this is a very confusing title for some of the young people in the audience, since to you it will look like I just wrote the same word twice. But if you look really carefully, this one has the infinity sound. Okay, so I'm going to start by talking about just operads without infinities. And so precisely what I mean by this in this lecture is that an operad is a symmetric operad with many objects, or also called colored operad. In sets. Then you could define more generally enriched operads, but sort of the behavior of the infinity operads that I want to introduce is that unenriched one, which quite parallels, in the classical world with operads enrichment sets. That's what I'm focusing on. So the basic idea of what these things are like is that an operad, in this sense, is a structure. It's like a category. In particular, it has many objects like a category. But multitudes are allowed to have several inputs. And then you have a symmetric part that tells you that you can compute these inputs. Make this a little more precise. An operad O has a set of objects, which are also symmetrical colors, which is where the term colored operad comes from. O, and then given the lists such objects, so line 1 through line n, and then another object x. We have a set of multi-morphisms whose inputs are minimized. And there's single object x. So if you think of this as a picture, we have a device, an operation that takes in this list of n things and outputs to be all. And here n is allowed to be 0, so it could have no inputs as well. Then we have composition operation. Right, so if I sort of abbreviate this whole list to y, then I can imagine I have a further list. I have my map, I only have from that list of y's to x, and then I have a bunch of further lists z1 through zn with maps p1, y1, instead of n to n. Then I should be able to compose these. This picture that I have y, and I have a bunch of z's. So if I have a situation like this, I should be able to compose this to a single morphism whose inputs are all the elements in these lists, and if that was trying to write out sort of I think if I actually write big G for the list of these G i's, let's say I have an operation that looks like F composed with a list, if you want to Gn, which goes from Z to X, so Z is the union of these Z1 for the. Okay, and then I can have an identity operation for the object. So that'll go from the list of length 1 with X. And then I'm supposed to be able to commute these inputs. So I'm given an element in the symmetric group sigma n. I have an isomorphism between the multiple morphisms, which puts 1 n X. And then I commute the y's according to my sig. Of course, this is compatibly with an application in symmetric group. And then the convolution should be, you might expect it should be associative. So we think of, well, F composed with the list G of operations, and then I compose that with another list, which runs with a chain. It's the same as F composed with, well, the list where I do like G1 composed with the chain. So it's sort of just associativity in the sense you get if you try and expand this picture to another level. So you stick a bunch of things on the left, and it should be a unique way of composing that whole kind of tree of operations into a single one. So condition is associative, it's unible. So if I compose with the identity, I get the identity. I take the identity plus the F on this side F, but also if I take F, compose it with a list of identities, F, and finally the position should be compatible with these symmetric relations. So this is sort of thing that's kind of annoying to write down, but it's, you know, that's the obvious thing that you and like, you know, this is a good first definition of an opera, but if you actually try and work with this hits at the fact that keeping track manually of these symmetric group actions is quite annoying. But you know, this is the idea that you can commute things. And so, you know, if I have this picture, and if I sort of, you know, if I commute the y's and then I commute the z's, I can sort of do it in, you know, either order, and it's just compatible. That's the idea. Right. So using notation, our operad just has a single object called, say, star. Then it's useful to write n for the multimorphisms with n, and so this will be, you know, list of n copies of star to star. And then in this case, this ON has an action of sigma n. And then composition will look like okay, you don't have row and one equal okay. Then I can compose. I have an operation with k inputs, and then I have a for each I an operation with ni inputs. And then compose to an operation with number because it's the sound. So what's the point of introducing these structures? Well, it's that you can use them to describe various algebraic structures, which, you know, so maybe is kind of overkill in the setting of sets, but becomes quite useful when we go to the infinity setting, where like working homotopy-coherently with algebraic structures really requires some kind of framework such as that of infinity operads to actually, you know, be possible to or to make them act like one. So let's briefly look at some examples of things we can describe. Using this, we first give some simple examples of operads. So we have con, the commutative operation. This is a single object. And then the unique analytic operation L n. And then it's like only one thing that the position can do, so I don't tell you what it does. Then we have the associative operad. So that again have the same object. The n operations are you describe as saying it's the set of orderings with n element set with the free sigma action on that. And then the composition is given by concatenating these orderings. Okay, so these are, you see one object operates before, you've certainly seen these examples. Let me also give a couple of examples where there's more than one color. Operad Cm, which would be the operad for modules over commutative algebra. So this will have two objects, A and N, and then the operations from this to Y to X will be this unique one if either Y is one of these, X is A. So that is, so that gives us a copy. If you look at that single object A, you get a copy of the commutative operand. But then there's also an operation if I have something that's of the form a bunch of A's, then a single N, output N. And so these operations are supposed to equal the action of the algebra on the module M. Then if I have something that's not of that form, I don't have anything. I guess I should say why is this it's of this form up to a permutation. Okay, and then so last example, Bn, which is the operand for bimodules over two associative algebras. So we will have two objects, L and R, and then so the operations with output L, you can think of it being the set of isomorphisms between X and that only consists of L's. So if X is not of this form, there are no operations, and then if it is of this form, we get a free action on all the possible ways of ordering the list. That will stay with R. And so these the single object things where I have only R or only L is supposed to give me 2 copies of the associative operad. And then things that output M. We're going to have isomorphisms in X and a bunch of L's, then a single M, and then a bunch of R's. Like if I have an input that looks like this, then I can sort of act by the things from L and things from R on the 2 different sides, and that's going to give me the bimodal structure. Okay. Another kind of example, if I have the symmetric monoidal category, and I can define operad version of it. So the operad. So the operad has the same objects. See? Then the operations input x1 for x7, input y, and actually the maps in V, whose source was the tensor product of the xi's, and the output is y. And then, the composition is given by tensoring together maps and then composing them. Of course, this is a little informal because, really, this you have to, if you want to make it precise, you have to be careful with how you sort of parenthesize the tensor product and use associativity isomorphisms and so on. But this really is well defined if you do that. Okay, so I said these things are supposed to encode various kinds of algebraic structures. So how do we do that? Well, we need to introduce a notion of a functor between operads. If I have 2 operads over T, functor of T is what you think it is, so we should assign. So I take f of x in P, where I know it's O, and then we should have some multimorphisms. In the objects, and then of course this should be compatible with position and identities and symmetric relations. Okay, so then we get category of Operads functors. So in a special case where the target is actually one of these operads coming from a symmetric monoidal category, then we often call functors and some O into the operad O algebras V. And so the point is that if we think of algebras in this definition, then the algebras for the examples I've written up here really are the structures I claimed they were supposed to be. So, for example, common algebra in V is the same thing as a commutative algebra update. Symmetric monoidal category V. So I don't want to go through this in full detail, but basically, I have a functor from com into V of. So com has a single object, it starts, and that has to go to some object A and B. And then I have a unique operation in on 0. That gives me a map from the empty tensor product, which is interpreted as nodal units. I have a map from the nodal unit to A. And then I have, well, in com1, I just have the identity of A. And then I have something in com2, which gives me a map from A tensor A. So that's my multiplication, and it's commutative because this was, this has to be compatible with the sigma n action, the sigma 2 action, which in this case does nothing here, and in this case commutes the 2 copies of A. And that tells me that if I commute the 2 copies of A, I'm supposed to get the same map as the one I had to start with. So that multiplication is commutative. And then the fact that there is a unique operation in com3 would tell me that this multiplication is associative because there's like 2 different ways of composing things, so they have to do the same thing because there's only one. So that's why this gives me a commutative algebra. Then you can look at the associative algebra, soft algebra, and the associative algebra. So the same as here, we have a single thing in com0. So like a single object. Some object V. Now from 0. Unit, but now if I look at the sub 2, I have 2 different maps, but they're, which is corresponding to the 2 orderings of 1 and 2. So it gives me 2 maps from A tensor A. But they have to be compatible with the sigma 2 actions. That says if I reorder the 2 copies of A, these 2 maps have to turn into each other. So that's saying that these 2 maps are given by multiplying in 2 different orders. And then again, from looking at a sub 3, you can show that this is associative as well. Okay, and then CM algebra B is the same thing as commutative algebra with a module. And the BM algebra is 2 associative algebras and the bottom. I guess if you haven't seen this before, it's a good exercise to think about why that's right. And then finally, if I have another symmetric monoidal category W, then W up algebra in V, it's the same thing as a max symmetric monoidal functor. In W2. So why is that? Well, if I have some multimorphism in W opt, And I can always divide W1 and then goes to W prime. I can always factor that as kind of the canonical map corresponding to the identity of the tensor product of the W's. And then some unary operation from that tensor product to this. And so if this is going to go to something in the operad, and my algebra called F, then this is going to go to something that goes from FW1, FWN to FW prime. But it has to factor like this, and it has to go through something from F W1 instead of WN. And then this map corresponds to this map now. It's the same thing as giving a map from the tensor product of the FWIs in V. The F of the tensor product. So this is like the structure you get from a lax symmetric monoidal functor, and this also determines the entire structure of the functor of Operads. So we can think of symmetric monoidal categories with lax symmetric monoidal functors as a special subclass of Operads and Operad functors. So this becomes like, classically people often just talk about one object Operads and then algebras for them in a symmetric monoidal category. But to get something that we can cleanly generalize to the infinity setting, it's quite important or quite useful that we see if we work with the colored Operads, we can really put one object Operads and symmetric monoidal things on the same footing. They're both examples of colored Operads. And so we just have to figure out a way to infinitify those to get the good notion of algebras and symmetric monoidal infinity. That's what I'm supposed to use.
We used to have these better, as you know, Rune, when you were here, Lars had the supply of Japanese soft cloths, but they're becoming scarce.
No. Almost. Okay, so that was a very quick introduction to Operads and sets. But if we want to make them into something that we can turn into, we can put an infinity in front of this. This is sort of not a very useful approach because we don't have to introduce this brand new kind of structure that is like in a category, but it has these other compositions and so on. So turns out there's a very useful way to think about Operads entirely within the world of ordinary categories, that when you put infinities in it becomes Lurie's approach to infinity Operads. So I want to start. The next thing I want to do is to introduce that description of Operads. So it's Operads described via the categories of operators. Here's the notation. So I'll write backward ball F derived from the category of finite sets. And then F star will be finite pointed sets. And within that, sometimes it's useful is to simplify the notation to pick a representatives for the isomorphism classes of objects. I'll use this angle bracket n notation to mean the set 0, 1, n, where 0 as the base point. And maybe I should say straight away as well, another description of this category. We can think of it as a category of. We can think of the objects as being just being finite sets, with the morphisms being partially defined functions. So I can map yes, T will be then some subset of S, and then I map from that subset into T, where S, the correspondence is that if I want, I added just on the base point, S and T, then I make a map of pointed sets by sending everything that is not in a 0 to the base point. It's not in the 0, it goes to the base point here. And then conversely, if I start with a map of pointed sets, I can look at the things in S that didn't go to the base point in T plus, and that gives me my S0, and then I have an actual function from that into T. So this is often a useful way to think about it. And by composing these things, you can think of it as taking like a sand composition. So I can literally take a pullback of T0 into S0, take my composition like that. But why is this relevant? It's because I want to define this category of operators. I believe this definition goes back to a paper of Thomasy. Well, I don't think they didn't use it to describe operads, but they did define this category and do good sweeping so that you find an operad O. Then let's see the category of operators. I will note as O. Let's see the category where the pointer choose anything with set. As this object, we give an object to define a pointed set. And then the list x1 to xn, objects in that graph. And then we define morphisms in the list n to y1 n by taking after first I apply the map of pointed sets from n to n. And then for every non-base point element in the target, from 1 to n, multimorphism with target yi, and the source is the collection of x's case such that there is a pre-image of I. So, in other words, a morphism is a list of multimorphisms in my operad with the target, but then I'm also allowed to throw away some of the inputs before I give it a list. So the idea of doing this is that we want to be able to turn the composition of multimorphisms in the operad into an ordinary composition in the same category. And then the map to finite pointed sets will tell us how to like decompose things again and recover the multimorphisms from the operads, from the morphisms here. And so keep on compose. Now if y and z1 to z-r, just given that find something sets, and then these multimorphisms phi and then here I have my find something sets with collections and group phi j of multimorphisms. Then, well, I'm going to go here. I'm going to try and do it again. I'm probably going to realize the number of six, but of course I can post my two maps and find a sense, fine, and then I want to take, I'm supposed to produce for each z1 through zr, I'm supposed to produce a multimorphism in my operad, and so I take the one I already had with phi zj, psi j, and that had as an input from list of yi's. Then for every yi I have in that list, I had multimorphism from some x's. So here I can take the collection of multimorphisms phi I, we'll build those i's, and the input will be a collection of x case, such that the pre-image on the little phi of each of these i's, which is the same thing as saying that k is in phi inverse of I. And so the point is that this is exactly, this is a list of multimorphisms, and this is a single one, and then I trust I can compose this stuff in the operad. So that's what I mean when I say we compose in such a way that we can turn composition of multimorphisms in the operad and code that as an ordinary composition by constructing this area. And then we can also see that the functor of operads E gives us a functor mechanically operating with O, mechanically operating with P over 526. Just by applying F, well, to the data of the categories. And so this actually gives us a functor from the category operators to ordinary categories over 506. So the idea now is that we can actually identify the image of this functor, and we can show that this functor identifies operads with a certain subcategory of this overcategory, and then we can characterize that subcategory without any reference to the notion of operad. And so this will give us a definition of operads just purely in terms of normal category theory, which In particular, we can easily generalize to the world of infinity categories because the way we'll describe it sort of has very natural analogs within the theory of infinity categories. So, I need some terminology. So, I say map F5 and then in tensors. Active if the pre-image of the base point is the base point. So in the partial map definition, this is saying I have n, then I just have actual function defining all of n going to n. So no non-base point elements are sent to the base point. It's the unit if well it's sort of so it's the opposite, so it only sends things to the base point and then it sort of it gets an isomorphism away from that. We can say isomorphism away from the base point. And then we'll say that the pre-image of I is size 1 if no base point. And then in the partial map definition, this is the case where we just have restriction to the subset. Then we don't. So we just give the identity on that subset. And so in the partial map definition, it's kind of clear that every map is a composition of an inert one followed by an active one. We restrict to the subset, and then we do a one-way map. And so this is a factorization system of final composites. I'm particularly interested in a certain collection of enough maps, rho I and to 1. And this is the map that will take J. Well, it goes to the base point unless J is equal to that. Or as a partial map, it's the inclusion of the subset. So, and you can sort of start with this terminology, you can sort of start to see how we recover the structure of the operads from the category of operators. So, we know there's unique, we can see there's unique active map. And 1. And then if I look at the maps in op O that live over this map, alpha n, those are exactly, if I have something over n, then over here, my definition tells me that I'm just supposed to supply a single n-ary operation in my operand. So morphism in O over alpha n is precisely an n-ary operation in my operand O. Generally, I have an active map M alpha, then morphism over alpha consists of a list of n multimorphisms with inputs of size and I, which is a pre-image of I, under alpha n of I. So this is a list of these multimorphisms, and then if I compose them, position over n to n alpha and then alpha n1, that's exactly giving me the composition of multimorphisms in the opera. So given this of O, I can recover the multimorphisms and the composition by looking over the active maps. But then what are the inert maps doing? They're the ones that tell me how I actually decompose a morphism into a list in this way. If I didn't know I already had that, I'm supposed to use the inert maps to get the decomposition. So I said that we could characterize the image of this functor from Operads into categories over finite pointed sets. So to state that characterization, I need a little more terminology. And every functor, P from E to D, then morphism F from Y to D, or P for Cartesian. If whenever I have another object, Z equals mutual square, I take common E from Z, common E from X to Z. This is composed from F. That's the sum to B using my functor P, so I have the constant Py to Pz, and it's from Px to Pz. This is composition of Pf. This is supposed to be a pullback. Usually with me, if I supply something here, some enough. If I supply something here, and also the same thing here, then there's a unique thing here. And so diagrammatically, that means that if I supply a map from X to Z, then I have my F, which is a map from X to Y. And this, so this level of Px, Z, Y. So I'm supposed to supply something from Py to Pz, but composes to give the image of this map from X to Z. So if I have this data, then there exists a unique map from Y to Z lifting this one. Then we'll say that E has Cartesian lifts. Some set. S of morphisms. That's primary update X and E. The map P of X, if from Px to B and S. There exists a P Cartesian morphism. Bar from X to some Y. That lifts F, so P of F bar. So we say that, for example, that P is a co-Cartesian vibration. Or more classically, a Gorton off vibration. If it has lifts of all morphisms, and so the minimal case we say that P is an iso vibration. You can ask them for isomorphisms. So for an isomorphism, the condition to the P co-Cartesian is kind of vacuous. So this is also to say that I can lift isomorphisms. And so now I have to explain that this is actually like a very evil and wrong definition, because I asserted that two objects in the category are equal. Namely, I said that, I said that P of Y should be equal to B. And of course, we're not really allowed to do that. We should really be making a more correct definition where we say that this is lifted up in isomorphism. But then I have to sort of do some two category stuff to make the next definitions come out. So I just don't want to do it. I'm going to do it the lazy way for now. And then once we put infinities in place, everything has to be done in the proper way. So it's working with one category is just evil to start with. So we'll be morally pure once we go to the infinity settings. Okay, and so in particular, like up to, so in particular, with this strict lift, the notion of vibrations is not invariant under equivalence. And so, for example, being an isovibration is sort of like being in a vibration in a model category, like any functor factors as an equivalence followed by an isovibration. I guess it's literally the vibrations in a model structure like categories. So I'm going to tell you what we shouldn't be saying. Okay. So I think I can illustrate the statement of the result.
Has it developed so that it's a swear word to say model category?
Okay. Only that an isovibration is equivalent over time constant to the category of operators of an operad. If and only if the following three conditions hold. First, I'm going to say that E has the Cartesian lifts. The node morphisms. So as I said, the node morphisms correspond to like the decompositions of my lists. And so having these Cartesian lists is what will tell us how to decompose things. And then the following condition are given x and e and the fiber over bracket n, and then for Cartesian morphisms I over rho I. So that is over there. So that's these are the inert maps from n to 1. And then if I have another object y in en, to say that using these Cartesian maps, so if we look back at the definition of O, these are going to be the ones that give me the projections from the list to its elements. So I want to say that a map from y to x decomposes into a bunch of maps y to inside. Okay, and then point 3, saying that given some list of objects,
The statement.
sorry?
The statement.
Oh, yeah. So this roughly speaking says that a map from y to x decomposes a list of maps from y to xi. There exists an object x b en with Cartesian morphisms. Let's do xi over. And we also say that our functor be prime over x comes from a functor of Operads if and only if f preserves the natural Cartesian function. So I'm really at the time. So kind of the upshot of this is that I can identify not as the subcategory of actual start with objects classify versions where the conditions 1 to 3 and morphisms prevailing in that Cartesian morphism. And so this gives me an alternative description of the category of operads. And I'll come back to this in a later lecture and try and explain a bit more where this condition 1 to 3 actually come from. But if we believe this, then what we've accomplished here is to give a description of operads purely within the world of ordinary categories. And we have some conditions that will be we can very naturally generalize to the infinity category setting. All we're using here is Cartesian morphisms and POMs, and that all has obvious analogs there. And so this gives us a way to to define infinity operads within the language of infinity categories that we've already developed, and then more. Yeah, okay, I'll stop it.
Any questions or other than yes, Austin, or others?
Yes. Annoying question. Why do you keep saying isofibration with inertial Cartesian ellipse and not just functor with inertial Cartesian ellipse?
I guess that's true, yeah, since isomorphisms will be in that. Okay.
I guess because in your head secretly the inertial Cartesian ellipse is replaced by the invariant condition.
I don't know. I think it's just like I know that I have to say isofibration, otherwise I should be putting like a natural isomorphism in the triangles. But yeah, it's implied by having enough convolution lists in this strict sense. Okay, are there other questions?
I had one question about Lurie.
Yeah, I don't think I should answer that one. I'm being recorded.
All right, let's thank Rune again.